The water is black at 4,000 meters. Not dark, not dim, black, the absolute extinction of light. Where pressure climbs to 600 atmospheres and the ocean floor becomes something closer to another planet than anything a human hand was built to touch. No current moves here. No sound travels the way sound was meant to travel. The seabed is cold beyond the vocabulary of cold, and it has been undisturbed for geological ages. Compressed sediment, volcanic rubble, the slow archaeological drift of things that sank and were forgotten. Then the cable comes. 800 tons of steel and hydraulic intention, dragged across the surface somewhere far above, feeding a machine the length of a city block down through the thermocline, past the mesopelagic, past the abyssal plain's first whispers, until its weighted plow makes contact with the seafloor at a velocity that sends plumes of silt mushrooming outward like slow explosions. The machine has no name that sailors trust. They call it the beast. They call it the trench. Some call it nothing at all, which is what you call something you have decided not to personify, because to name a thing is to believe it can be reasoned with. It cannot. What the engineers called a submarine cable laying and ocean floor trenching system, what the Admiralty called a strategic infrastructure asset, what the shareholders called a return on capital. It mapped the ocean floor with greater precision than any vessel before it. It laid communication cable across 4 continental shelves. It opened the deep ocean to industrial ambition in ways that rewrote the geopolitical order of underwater infrastructure. It also dragged 11 men to their deaths across 3 separate deployments, snapped 4 kilometers of armored cable in a single catastrophic event, and was eventually abandoned, not decommissioned, not retired, not ceremonially scrapped. Abandoned on a gravel bank off the Faroe Islands, where it has sat for decades, rusting back into the element it was built to master. This is not a story about failure. It is not a story about success. It is a story about the particular madness of industrial ambition. The moment when human beings decide that the deep ocean is a problem to be solved, and what the deep ocean does in response. Here is the paradox that no engineering report will state plainly. The machine that killed men was also the machine that made modern communication possible. Every transatlantic telephone call placed between 1962 and 1991. Every financial transaction cleared between London and New York before the age of satellite redundancy. Every military signal transmitted beneath the ocean surface during the tensest decades of the Cold War. All of it depended, at some point in its infrastructure chain, on cable laid by vessels operating systems like this one. Systems that were fundamentally, structurally, knowingly dangerous to the men who operated them. The question, the one that sits at the center of this machine's story like a fault line beneath a city, is this. At what point does the map-making of an unknown world justify the cost of the men it consumes? The ocean floor was genuinely unmapped. The strategic necessity was genuinely real, and the machine was genuinely extraordinary. To understand why this machine was built, you must understand what the world looked like in the decade before it was commissioned. It is 1954. The Korean War has ended without resolution. The Soviet Union has detonated its first thermonuclear device. NATO's strategic planners are working from a single, consolidating fear that in the event of open conflict, surface communication infrastructure will be destroyed within the first 72 hours. Radio signals can be jammed. Aerial cables can be bombed. Land-based relay stations are soft targets, mapped and cataloged in enemy intelligence files with clinical precision. The ocean floor cannot be bombed. Not yet. What lay beneath the Atlantic was therefore not merely an engineering frontier, it was a strategic sanctuary. If reliable cable could be laid at sufficient depth, below the thermal layers that distorted signal, below the depth charges and the submarine traffic, below the operational ceiling of any weapon then in existence, communication between Allied capitals could survive a first strike. The British Admiralty and the American Office of Naval Research reached the same conclusion independently. The deep ocean floor must be mapped, armored cable must be laid across it, and the vessel capable of doing both simultaneously did not yet exist. It would have to be built. The contracts were drafted in 1957. 800 tons of operational displacement. Hydraulic trenching capacity to 4,000 meters. Cable storage for 600 kilometers of armored line. a deployment timeline that left no room for extended trials. The Cold War did not wait for engineering confidence. The shipyard at Barrow-in-Furness in the winter of 1957 was noise and scale. Arc welders burning at temperatures that turned steel into liquid light, hydraulic presses stamping hull sections that weighed more than most buildings, cranes swinging load after load across a yard that employed 6,000 men across 3 rotating shifts and never, in any hour of any day, fell silent. Into this came the specifications for hull reference 7 Tango. The trenching mechanism alone required 18 months of prototype development. To lay cable at depth, the cable must first be buried, protected from trawler anchors, seismic movement, the slow abrasive drift of deep ocean current across exposed armoring. Burying cable at 4,000 meters meant dragging a plow across a seafloor no human eye had ever seen, through sediment whose composition was known only through core samples from vessels operating at 1/10 the industrial scale now demanded. The engineers solved the problem the way engineers of that era solved most problems, with more force. The trenching plow weighed 41 tons unloaded, connected to the surface vessel by a composite cable assembly. Steel armoring around a copper signal core around a tensioned polyethylene sleeve that had to simultaneously bear mechanical load, transmit seafloor sensor data, and survive pressures that compressed standard materials to structural failure. It took 4 iterations and 2 catastrophic test failures before the assembly held. When hull reference 7 Tango launched in March 1961, the yard's superintendent wrote that the vessel represented the outer boundary of what current materials science could sustain. He meant it as a compliment. In retrospect, it reads as a warning. To understand how the machine worked is to understand precisely how it could kill. The surface vessel sat above the target trench line while the plow descended on its cable assembly through the water column. A descent taking between 4 and 6 hours. The cable paid out from a hydraulic drum system mounted amidships, a drum the diameter of a 2-story building, driven by a motor producing torque the yard's senior engineer described as, without exaggeration, geological. Once the plow contacted the seafloor, the vessel began forward transit at between 0.4 and 0.8 knots, barely perceptible from the deck. But at the end of 4,000 meters of cable, translated into a horizontal drag force of between 60 and 90 metric tons sustained across the seafloor. The composite cable assembly operated permanently at between 70 and 84% of its rated tensile load. This was documented as an acceptable operational parameter, a calculation assuming seafloor conditions would remain within the variance range established by pre-deployment core sampling. The deep ocean floor does not recognize variance ranges. The flaw was hidden the way structural danger is most reliably hidden, inside a number that looked acceptable until the conditions that made it unacceptable arrived. The composite cable's rated tensile strength had been calculated using static load testing in controlled dry dock conditions at ambient temperature. The figure, a maximum safe working load of 112 metric tons, was accepted by the Admiralty's Engineering Review Board without amendment in 1960. What the testing did not replicate was the behavior of the polyethylene sleeve at 4,000 meters depth and 2 degrees Celsius over sustained operational periods exceeding 48 hours. At that temperature, under that pressure, the sleeve contracted, compressing the copper signal core by fractions of a millimeter per meter of cable length, introducing internal stress concentrations the armoring was not designed to absorb. Over 4,000 meters of cable, fractions become meters. Internal stress concentrations become structural prefractures. The first officer to formally document this was Lieutenant Commander Hargreaves during the vessel's second North Atlantic deployment in 1963. His report was precise and unambiguous. The cable assembly was operating in conditions that systematically reduced its effective tensile capacity by between 18 and 23% below rated specification. The report was received. It was logged. It was forwarded to the Admiralty's Technical Review Committee. The third deployment was authorized 6 weeks later without modification to the cable assembly, without reduction in operational depth parameters, and without communication to the deck crew of Hargreaves' findings. Hargreaves requested a transfer. It was granted. The men who replaced him went to sea with a number 112 metric tons. That was no longer true. The system's actual failure threshold, in real conditions, at real depth, was somewhere between 87 and 91 metric tons. Standard operational cable tension during deep trench deployment, 84 metric tons. The margin was 6 metric tons, at 4,000 meters, in the North Atlantic. In February, the men who worked the cable deck did not speak much about what they did, not from secrecy, but because the work occupied a register of physical experience that ordinary language was not built to carry. The North Atlantic in February produces seas between 4 and 7 meters in significant wave height during standard weather systems. The abyssal carrier rolled at angles that sent unsecured equipment across steel plating with enough force to break bone. It pitched into troughs that placed the bow 15 meters below the stern for intervals long enough to feel permanent. And through all of it, the hydraulic drum continued turning. The cable continued paying out, and the men on deck continued their work, because 4,000 meters of suspended cable and 41 tons of seafloor plow did not respond to weather delays. 8 men per rotation. Their function was monitoring. Watching the cable assembly at the stern roller, watching the tension gauges, watching each other for the cognitive deterioration that cold and exhaustion and sustained mechanical noise produced in men awake for 9 hours in conditions that compressed experience into something geologically dense. They wore hearing protection that reduced the drum's operational noise from 134 decibels to a sustained 94. Still above the threshold of cumulative hearing damage, still loud enough that communication required a hand on a shoulder, a mouth close to an ear. They received no hazard supplement for cable deck assignment until 1966, 3 years after Hargreaves' report, 2 years after the first fatality. The supplement amounted to 4 shillings and 6 pence per operational day. 4 shillings and 6 pence. For standing 6 meters from a cable assembly operating 7% below its actual failure threshold, monitoring a tension gauge, displaying a number the Admiralty knew was optimistic. The medical officer recommended rotation length reduction to 8 hours. The recommendation was not implemented. It happened on the 14th day of the third deployment. February 19, 1964. 3.47 hours ship's time. Sea state 5. Significant wave height 6.2 meters. Wind from the northwest at 31 knots. The vessel was running at 0.6 knots along a pre-plotted trench line in the North Atlantic's Rockall Trough, at a working depth of 3,840 meters. Cable tension was reading 86 metric tons, within the range the crew had been trained to consider unremarkable. The plow had encountered a subsurface basaltic shelf. The seafloor sonar had not detected it. It rose from the abyssal plain at an angle of 31 degrees, a geological formation undisturbed for approximately 40 million years, struck by the plow with the full momentum of an 800-ton vessel transmitted through 3,840 meters of composite cable. The plow stopped. The vessel did not. The tension gauge moved from 86 metric tons to beyond its maximum marked graduation in less than 4 seconds. The hydraulic brake engaged at 104 metric tons as designed. It held for approximately 1.8 seconds. Then the cable assembly failed, not at the plow, not at the drum, but at a stress concentration point 340 meters above the seafloor, precisely where Hargreaves' calculations predicted the internal pre-fracturing would be most advanced. It unraveled under tension, armoring strands separating sequentially, each transferring its load to the remaining assembly, until the final copper core snapped and 340 meters of cable, approximately 9 metric tons, was released from tension and began its ascent. Physics does not negotiate. The surviving assembly breached the surface 30 meters off the vessel's stern at 63 kilometers per hour. It crossed the cable deck in a horizontal arc. The 8 men of the rotation watch had between 0.6 and 0.9 seconds from the moment of audible warning to react. 3 men were below the arc. They survived with injuries. 3 men were at the arc's periphery. 2 survived. 1 did not. 2 men were at its center. The inquiry recorded the event as a catastrophic cable assembly failure resulting in fatal deck incidents involving 2 crew members, with 1 additional fatality during recovery operations. 3 men. In 14 minutes. In the dark, in the North Atlantic, the vessel completed its deployment. The inquiry convened in Portsmouth in April 1964 lasted 11 days. Its conclusions managed to distribute responsibility so precisely across so many departments, review committees, and procurement chains that it effectively concentrated on no one. This was not accidental. The central documentary hazard was Hargreaves' report, acknowledged as accurate in its technical findings by 3 separate expert witnesses. It changed nothing about the inquiry's final apportionment of responsibility. The official finding was equipment failure under conditions exceeding design parameters, a determination that obscured the operational truth. Those conditions were the standard conditions of every deployment since commissioning. They had been documented, and the documentation had been absorbed into the administrative body of the Admiralty and rendered inert. The 27 recommendations were implemented selectively. Cable assembly testing was revised to include low-temperature pressure simulation. Tension gauges were recalibrated. Rotation length was reduced from 12 hours to 10, not 8, 10. Then the vessel was recommissioned. Because the cable still needed laying. Because the Cold War's appetite for submarine infrastructure did not pause for inquiries in Portsmouth. And because 3 deaths in 1964 had not altered the strategic logic that commissioned the vessel in 1957. They had merely been documented alongside it. The vessel laid 1,200 kilometers of armored cable across the Iceland-Faroe Ridge. It produced seafloor topographic data classified until 1987. It mapped a section of the abyssal plain later determined to contain hydrocarbon formations worth approximately £14 billion in 1990 valuations. 8 more men were injured across subsequent deployments, none fatally. The distinction between that outcome and 1964 was, by the vessel's own engineering officers, substantially a matter of fortune rather than design. In 1976, the vessel was towed to a gravel bank off the Faroe Islands and moored pending a disposal decision that was never formally made. The disposal decision is still pending. The gravel bank is called Fuglafjord, the Fjord of Birds. In summer, Arctic terns nest on the shoreline rocks within sight of the rusting hull. They were nesting there before the vessel arrived. They will nest there after it is gone. The abyssal carrier sits at a 15-degree list to port. Its hydraulic drum assembly is still visible amidships. The stern roller over which 4,000 meters of cable once paid out into darkness is still in place. The tension gauges on the drum housing are still mounted where they were recalibrated after Portsmouth. They read 0 now. They have read 0 for 50 years. The seafloor topographic data the vessel produced contributed directly to the routing of the transatlantic fiber optic cable systems, now carrying approximately 97% of all international internet traffic. The communication cables it laid maintained Allied strategic connectivity through the most dangerous decades of the 20th century. These are not small things. They are not offered as consolation. They are offered as the complete and unresolved picture. The thing that industrial history demands we hold in full. The men who died were not sacrificed for nothing. They were also not sacrificed with the informed consent that dignity requires. Those 2 facts exist simultaneously, without resolution, in the same historical record. The machine held both. It mapped the ocean and it dragged men into the dark. Hargreaves died in 1998. He had left the Navy in 1964. The same year his report failed to prevent what it had predicted. He became a secondary school mathematics teacher in Dorset and did not, by any account available, speak publicly about the vessel again. He taught trigonometry and probability for 31 years. He understood the mathematics of margins. He understood what 6 metric tons meant at 4,000 meters in the February North Atlantic. He chose to teach other people's children how numbers behave in the world. Perhaps that is its own kind of answer. The terns nest at Fuglafjord. The hull lists at 15 degrees. The ocean floor that the machine mapped in darkness, at cost, remains below. Still cold, still pressured, still indifferent, threaded now with fiber optic cable carrying the accumulated signal of the modern world through the same abyssal channels the plow first cut, through sediment still bearing, somewhere in its compressed geological memory, the shape of a 41-ton steel blade that passed through it once, dragged by ambition. In the service of a world that needed the map more than it admitted it needed the men.